Here's a tutorial on the atomic structure quiz, at least one version of it. This was not supposed to be 6. It has to be 7 because nitrogen has 7 protons. It can't be 6. 6 is carbon. So that was basically a free point for everyone. If it has 7 protons, then the rest of the total particles in the nucleus, which is what this is, must be neutrons. 14 neutrons and protons in the nucleus. 7 of them are protons. The rest of them, subtract, must be the neutrons. Same thing goes for this one, except silicon is element 14. If there are 28 total particles in the nucleus and 14 of them are protons, the rest of them, subtract, must be the neutrons. The neutrons match the protons a lot of time at the top of the chart. Toward the bottom, it gets less and less true, and it's after somewhere in, I don't know, somewhere maybe like argon or so, it's almost never true after that. At least down here maybe, and so on. An element is defined by only one thing, the number of protons, period. And I know I keep saying there's like an exception to everything I say, but not that one. 9 protons is fluorine, 10 protons is neon, period. End of story, always, yes, always. No, there's not an exception of any kind ever. Neutrons sometimes change and electrons come and go all the time, which is, geez, about half the content of this course seemingly is the electrons coming and going in certain ways. But if it has 8 protons, it's oxygen. And if it has 26 protons, it is iron. So on line 7, we get sulfur with 18 electrons and mass 32. Okay, sulfur. Well, might be hard to find, but sulfur is element 16. So it has 16 protons. The name for that in English is the atomic number. This number must match this number. It must match. There is no way for them not to match. This is just the name for that. If this is the mass number, again, like we did up here, by subtraction, 32 minus 16, we get that there are 18 neutrons. This matches that just by coincidence. Don't go by that. These do not have to match. Look, they don't have to match. But if we have 16 positive protons, because that's what sulfur is, and I'm telling you, hey, there are 18 negative electrons, then there are 18 negatives and 16 positives, and that means the charge is -2, -2. Also, the symbol is S for sulfur. 26 protons, we already said, is iron, Fe, iron. Is it charged 0, 1, 2, 3, 4? Well, let's see. Well, the mass number is 56, okay? If the mass number is 56, by subtraction of the protons, we get the neutrons as 30. This must match this. If there are, there's no indication that this is a charged particle, so I guess it's neutral. And if it's neutral, for every positive, there is 1 negative. So these match and the charge is 0. You could put a 0 here, but no one does. This one, however, tells you it's +2. And what is SR? Well, it's over here. It's strontium, SR, strontium. So SR, strontium. And it was element 38. So 38 protons and 38 atomic number. By subtraction, that this minus this, that gives me 50 neutrons. If it's +2 and you have 38 positives, how many negatives do you need? 2 fewer negatives than whatever the positives was, so that you get a +2 charge. The reason that this table is this shape is so that you can do the find the valence electrons. It goes like this: 1 valence, 2 valence, skip the middle, 3, 4, 5, 6, 7, 8. So carbon has 4 valence, 5, 6. What do we need? Nitrogen and neon. So 5, 6, 7, 8. So 5 and 8 valence electrons. What's different about isotopes? Isotopes change something about the element. What we can't change is the protons. That has to be the same, right? So the same is the protons, and we said the atomic number is the same thing. And neutrons are neutral. They don't really affect the electrons, so the electrons are the same. It doesn't matter what isotope it is. What's different about the isotopes is the neutrons. And if they're different, then the mass number must be different. Every element past lead is radioactive, and just a point for all my favorite nerds out there, what I mean is that apparently there is a method to stability in the nucleus. Kind of like there are energy levels for the electrons, I'm told that there are sort of energy levels in the nucleus is the current theory, it's the current explanation for how they act. And for reasons no one ever got into with me, is 82 protons is the max number before everything is just unstable. If you have 83 or above, that nucleus is unhappy, very little to quite a lot, but unhappy, and it will be radioactive at least a little bit. So every element past lead is radioactive. And uranium is the last natural element. I'm guessing what they mean really, if you want to get really drilled down into it, is that the supernovas that make all the iron and osmium and platinum and gold and mercury and lead and so forth can only cram those protons together up to 92. And even if they can get 93 or 94, I don't know for sure, maybe they can. In any case, if they can, then this stuff is so radioactive that it's gone by now. Anyway, uranium is the last natural element, and I think that means that has ever been observed in something that wasn't man-made in the past 60 years or so.